Swayam Prabha. Digital India. Educated India.
Okay, that's fine. So, yeah, so today we will basically summarize what we have been doing in the last 40 odd classes. I will start by before we collectively recollect, right, what we have done so far. I will just sort of make an observation on what we have been doing so far. Okay. So, though it is supposed to be computational fluid dynamics, an introduction to computational fluid dynamics, you realize that basically what we have done is we have looked at ways by which we can solve differential equations, right, and variational problems, how to represent them on the computer and how to get solutions of a numerical nature. Okay, so I want to put that in some kind of a context, in a context, in the sense that now I want to make it a very broad context. So far we have been acting as though it is fluid dynamics, but if you think about it, I have not really mentioned fluids that much. Maybe I have mentioned a little gas dynamics along the way, right. I mean, but we have not really the equations were not like the full-fledged fluid equations or whatever. We have looked at Euler equations and so on, okay, right. So just to put that in context, I want to graphically show you something about the nature of how these things work, okay, just a big picture, just a big picture. So on the one hand, okay, I have I will maybe even color this, I will color it, I will fill it inside. On the one hand, that picture is supposed to represent reality as it is, right, what we are trying to model as it is. And if I am able to reproduce it, but if I am not able to reproduce it exactly, it does not matter. Okay, so I will say, does that make sense? And from here to here, now I am going to write processes. Okay, this is perception, this is what we see. Perception, that is what we see, whether you use a microscope to see or whether you use right, whether you just look. When we talked about deriving the governing equations in one of the classes, I sort of waved my hands around and said molecules, what molecules, no molecules, right. I do not see the molecules. Am I making sense? We may be able to infer that they are there, but a phenomenological attitude would be continue, it is continuous media around, okay. So that would be perception. This is what we see, and the trouble with perception is there is a lot of detail. I mean, benches, carpeting, I mean, a lot of detail, lot of fine grained detail. We can't handle that much detail. Okay, so even from what so there are things that we don't see, that there are things that we just can't see. I mean, we are unlikely to see the locations of every molecule at every point at a given instant. You know, it's not going to work. So we come up with, we throw away what we think is the detail, we throw away the details and come out with a mathematical model. And for a mathematical model, of course, what am I going to choose is the geometrical shape, as close a circle as I can get, right. So we come up with a mathematical model. Okay, so this is a big picture of what we are doing. There is the reality, there is what we see, can't handle the detail, mathematical model. And very often, as in the case of the Navier-Stokes equations and so on, can't handle the mathematical model. Okay. So then we go, where do we go? Then we go to the computer. Okay. So this is deliberately, of course, it clearly geometrically supposed to represent the fact that this has an infinite number of sides that has only a finite number of sides. So one of the things that we have looked at is, for instance, we asked the question of consistency. So if the number of sides keep increasing, does this become the circle, right? Does the solution go, does the model go? There are questions that we have asked. So there is an issue of verifying that this is indeed this. You have written a program, right? So actually I just say computer model, this itself you can add levels. There is the chalk dust that we write, right, of the finite difference scheme or whatever. Then there is the actual program, which is a representation of that algorithm, actual representation of the algorithm on that particular computer. And then there is the issue of whether does that represent the algorithm that you set out to implement, does this become this, you understand, or does it, you may want to verify whether that is correct. So you can verify whether this is correct. This is called, very often this is called validation, okay, right. From here to here, of course, we actually called it consistency. You understand what I am saying? So this is sort of the big picture. This is what we have, this is what we see, this is what we are hoping we can do. This is a mathematical language. This is the abstraction from this. Abstract basically means to extract, right? You abstract out the essentials and throw away the non-essentials. And if by chance you throw away something that's an essential, that's a different story. But you throw away, you abstract out the essentials, and you don't worry, that because that's how science works. The science works on generalities. Science works on things that are common. The particular is of no interest to science. We want to make a general statement, right? We are not, the particular is of no interest to us, right? So we abstract out the general, and very often we find that this, we can't solve this, right? This is where we are. So actual fluid, what we see, Navier-Stokes equations, finite difference method, that is one way to look at it. Is that fine? Okay, everyone? Okay. So as I said, I just wanted to talk about this so that we had this, we have this general context in which we can look at the course and possibly some of the material that you have seen elsewhere. So why don't we see if we are able to do a review of the material that we have covered so far. Okay, fine. Where did we start? We have about 40 odd minutes in which we can cover the 1 minute per day is essentially where we are, right. So where did we start? What was the start?
Representation of numbers.
Yeah, so we basically said that we started off with the idea that the problems that we are solving have solutions which are functions. If you remember, the problems that we are solving have solutions which are functions. So we need to be able to represent functions on the computer, right. So we sort of realized that, oh, we have to be able to represent things on the computer. So towards that end we basically said that let us see how things are represented on the computer. Okay, that's where we, so that was the motivation. All the equations that we solve typically end up being, the solutions end up being what we mean when we solve. It is not like x squared equals 2, therefore x is square root of 2, right. So you get a nice number, whereas what we have are more like functional equations, equations for which the solutions are functions. And we basically said, oh, if I want to solve that on a computer, then I need to be able to represent the solution on the computer, I need to be able to represent the problem on the computer. So how does one represent things on the computer, right? And we started by saying how do we represent, well, integers. Computers are good at representing integers. How do you represent the real line? And computers aren't good at representing the real line. That is what we found, right at the real line. We found that the computers aren't good at representing the real line, right. So the real line was the first time that we encountered a form of representation error called floating point round off error, right. So of course there is fixed point and floating point. I will just mention that since I inadvertently said floating point. So you have fixed point representation and floating point representation. Fixed point representation is just like dealing with integers. It is just like having an integer and assuming the decimal point is at a set point. Floating point, of course, the decimal point in theory moves because you have an exponent, fine, right. So the representation error, so one of the things that you have to take from this course, the representation error in numbers has a special name, it is called round off error. Okay, so anytime you are basically asked, oh, what is the error that you get, And the round off error, what is the round off error? Round off error is the difference between the number and its representation on that computer, okay. So and that computer could be a piece of paper, you decide that you are going to represent a number using 3 decimal places, then you are the computer, right, and then that's 3 decimal places, right, is what you are going to have, and therefore that would be the difference. Now if you read, and I can see smiles, but if you read old books, when they say the computer should be careful, they really mean you, right. So you go back and get a numerical analysis book from 1940s or whatever, and they are saying the computer should be careful, they really do mean you as the individual doing the computing, okay, fine, right. So that is as far as representing numbers goes, and once we said we can represent numbers, obviously we look at other mathematical entities, and an obvious mathematical entity that we have is a vector or an array. An array is a general idea in computers, so whether you can represent vectors and matrices, okay, you can represent matrices, but if you want, most programming languages will not do the matrix algebra, they will not do the matrix addition, you have to do it, okay, most programming languages will not do that for you, there may be a few that do it, but most will not do it for you, okay, right. So it is possible, and how did we represent matrices? So we represented matrices and vectors by basically, well, vectors we represented by basically locating in memory in a sequential fashion, right. We were able to say that there are so the 1, 2, 3, 4, 5, 6, 7 elements, right, placed adjacent to each other could represent a vector, right, in a one dimensional array inherently. So I am using the term array, right, and of course if you wanted to go get a matrix, you could then stack one on top of the other, okay, that was the idea, right. So it is actually possible to get a single subscript object AI or a double subscript object Aij, okay, or even a triple subscripted object and so on, and then what you do is you take whatever it is that you have stacked in the second dimension, you would stack it in the third dimension. So then you know that you can actually create multi-dimensional arrays, it is actually possible to create multi-dimensional arrays, is that fine, okay. So by now what we have done is we have managed to represent integers, numbers, real line, we are able to represent then using those integers and real numbers, so to speak, real line, we are able to represent matrices or arrays, right, one dimensional arrays, 2 dimensional arrays, multi-dimensional arrays. So the second thing to do is now we have to state where we are talking about representing functions, right. So what did we do after that, how did we go about that? We did a little, we set up we looked for function bases, so we did a little review of vector algebra, right. We showed how we constructed vectors in the normal vector algebra. When I say vector algebra, the algebra that you learn in your college, we did a little vector algebra and showed that, well, if you had the dot product, it was enough for you to actually construct, okay, it was enough for you to actually construct a set of basis vectors and so on, given a linearly independent set of vectors that span that space that you are interested in, okay. So what we did was we constructed box functions, and here this was the first thing that we did, we constructed box functions. So the box functions were two of two kinds. We constructed a box function f and g. I am not going to do all the details, as I said, though it is a quick recollect, right. We constructed box functions f and g, and basically said that on non-overlapping intervals, if the box function is 0, right, in this case it is 0 here, and the intervals do not overlap. Remember, wherever the function is non-zero, it is called the domain, part of the domain where the function is non-zero is called the support of the domain, okay. So the supports of the support of the function, the supports of the two functions are non-overlapping, and the functions turn out to be orthogonal. That is one way to get orthogonality. The other way that you get orthogonality is that the functions somehow change signs appropriately, right, like trig functions, sin x and cosine x, right, occupy the same interval, they are defined on the same interval 0 to 2 pi, but they are still orthogonal to each other, okay, right. So we were able to show that we could represent functions using function basis using the box function, and we saw again that there is a representation error, okay, we again saw that there was a representation error. For the box function we asked ourselves the question, what is the nature of the representation error? The reason why we ask ourselves what is the error, that question is important, is can I get an idea of what is the error, because if you know what is the error you can then try to get an idea as to where the error is coming from, and then there is scope for improvement. Okay. So as I keep repeating, it is not just enough that what we do, that those are skills, but you should also see there is a higher level skill that you have to aim at. You have to look at the process that we are going through, right. So you always ask, so you do something, then you have to ask the question, how good is it? Is there a way that I can get an idea as how good is it, because the minute you are able to quantify it, then there is scope for improvement. Okay, that is very important. So we ask the question, this representation error, and then our analysis basically showed, I mean these are constant, so you can represent constant functions exactly and nothing else. Okay. So basically what we then did was we said we will go to higher order polynomials. Of course one of the disadvantages this had was that a representation using box function, what was the bad thing that it had? You had a lot of jumps. You had a lot of jumps. So in fact I think I used a straight line. You get a lot of jumps, they are non-overlapping, so I have to make sure that you get a lot of jumps. The function is very jumpy. You can get closer and closer to the solution, but the function just gets jumpier and jumpier. Okay. The alternative to this was saying that, well, we got orthogonality this way, but we know that using something like the Gram-Schmidt process or whatever, right, we could make functions, you can come up with an independent set even if they are overlapping. So we looked at the set of polynomials 1x, x squared and so on, okay, on an interval. We have to specify the interval on an interval. So on -1 to +1, for instance, 1 and x are orthogonal to each other. On 0 to 1 they are not. If they are not orthogonal to each other, you can subtract from x its projection on 1 and get an orthogonal set. You understand what I am saying? And then you can build up an orthogonal set using this, that is what we saw, right. However, just like sin x, cosine x and so on, this has a problem. So if on the whole interval on which you are trying to represent a function, you represent the function using a series, a 1x, x squared and so on, or an orthogonal set formed from it, any change in coefficient will change the function on the whole domain, whereas box functions have something called locality, right. So I want to recollect that locality. Box functions have something called locality, which allows you to locally change the value, locally move the function value, the representation, without affecting anything elsewhere, okay, right. So now we are able to represent functions. We basically combined this idea, this with the non-overlapping what should I say intervals or supports to construct hat functions, to construct functions that look like this. I just call it f, to construct hat functions, okay. The hat function was 1 at the node at which it is defined and 0 at the adjacent grid points, okay, 0 at the adjacent grid point. Is that fine everyone? Okay. So we were then able to get linear interpolants, we were able to get linear interpolants. However, what was the disadvantage? That you have overlap of adjacent, right, which can create interesting things like in the last but one class, right, it can create interesting situations, okay, but you have overlap and it is always a problem. See, orthogonality, that is the reason why we seek orthogonality, because otherwise you do not have, right, but on the other hand you get linear, and we saw that you could do not only linear, you can do quadratic, you can do cubic. Am I making sense, right? So you can, your interpolants, your basis functions can be any order that you choose. There are many ways by which we can choose it, okay. So I think I mentioned quadratic and I did cubic in class, right, if I remember right, okay. What else did we do? What did we do after that? We got an estimate of the representation error here. Then we basically turned around and said, well, if I know the function I can use this for a representation, but what if I do not know the function ahead of time? That was the motivation that I used, okay. If I do not know the function ahead of time, what do I do, right? So then we used Taylor series and we came up with a finite difference representation. So I am not, the finite difference representation of course basically made use of the fact I am not going to use i's and j's as the indices, I am going to just make a general statement, made use of the fact that if you have the function value f of b and you have the function value f of a, then what is fb minus fa divided by b minus a. This looks like something from mean value theorem, right. So mean value theorem says that there is some point in between, some point unknown location psi at which this is the exact derivative, right, for a continuous function there. Now what we know is that if I represent this using Taylor series, if I represent this, if I say, see, fb minus fa divided by b minus a is a number, right, is a number, just say it is 2. So you calculate this and you get the answer 2. What it basically says is, if you say 2 is the derivative there, the representation is first order representation, the error is proportional to b minus a. If you assume that it is the derivative there, if you say 2 is the derivative there, that is the approximation that you are making, right, that is the approximation that you are making, then the representation is first order, right, the representation is still first order, the sign of the error changes, and if you assume that it is the representation of the derivative, the same number 2, if you assume that it is the derivative at the midpoint, then the error becomes second order, b minus a whole squared, okay, is that fine. So here it turns out that the derivative corresponds to the function being represented by linear, and there it is actually quadratic, okay, you look at the term, it is as though the function is represented by a quadratic, even though it is actually you have drawn a straight line, okay. So the same number, and as I said, unfortunately mean value theorem says that at some unknown point it is exact, but we do not know, that is the whole deal, right. So at some unknown point in between it is exactly the right, it is, and you know, we are looking at it graphically, you can just basically say, oh, it is most probably at that point, right, graphically yes, but in reality we do not know what it is. So that is basically the idea of, so finite differences, and we found the truncation error using Taylor series, right, truncation error. So I introduced that term, truncation error is if you have an infinite series, you truncate, you throw away, you eliminate all the higher order terms and retain only the leading terms. The error that you make doing that is called truncation error. What else did we do after that? What was the, once we have finite difference represented, so we can represent first derivatives, second derivatives, we figured out, we showed that we could represent higher order derivatives, right. Then we turned around and said, okay, why do not we apply it to solving an equation, and we took Laplace's equation as the start, right, and Laplace's equation was relatively easy, Laplace's equation is relatively easy, and we basically showed that Laplace's equation, nabla squared phi equals 0, this is an equation that I have written many times many times in this class. So you could do, right, phi at p cube was a quarter of basically the average of the neighbors, okay, summation neighbors, right, neighboring phis, summation, so it is average of the neighbors. Laplace's equation turned out to be averaging of the neighbors, and we use that fact that it was averaging to actually show that, what did we show? We showed that, yeah, the solution is unique, you understand that two of you can't get two different answers and so on, right, that the solution is unique. We use that averaging to show that there is a principle called maximum principle that it satisfies, that the maximum and minimum in this case actually occurs on the boundary, okay. We proved as a consequence that maximum and minimum occur on the boundary, am I making sense, and use that to then show that the solution was unique. For the numerical case, you may have seen for the continuous case, for the discrete case, we showed it only for the discrete case, okay. So what else did we do with Laplace's equation? What did we do next? We looked at some acceleration schemes, in particular we looked at SOR. So we basically said that, well, if you have a phi that comes from this, instead of calling it phi n plus 1, we called it phi star, and it is possible to take a linear combination of the proposed solution and the current solution. So to get phi n plus 1, you could get omega times phi star plus 1 minus omega times the old one, okay, and we looked for ways by which we could find omega, the optimal omega. Like we said, this is a situation where we are looking for non-uniform convergence. If it is uniform convergence, then omega, it does not help. We want, as a function of, we want the convergence rate to change as omega, and we found that there is actually a way to find the optimal omega, okay, by systematically hunting. There is no analytic method by which you can do it, but you can systematically hunt for a optimal omega. Is that fine? We also showed that solving this was the same as solving a system of equations. Solving this is the same as solving a system of equations. So we had what? We showed that it was the same as solving x tilde equals b tilde, right, which was the same as minimizing a functional q of x tilde equals minus 1/2 or 1/2, it depends which way you want to take it, x tilde transpose A x tilde minus B x tilde B x transpose B, because I think I did that at least twice, we went through some interesting errors there, but anyway it is fine, okay. So we basically showed that this was minimizing this, right, it is the same, minimizing this is the same as solving that. A, remember, is symmetric, that is an important property here. A is symmetric, A equals A transpose, A is symmetric, okay, A is symmetric, and there are some interesting properties, but anyway we won't worry about it. And we showed for SOR, as a consequence, y omega has to be in the interval in the range 0 2, so that we got an idea that we have to pick omega within the range for this linear equation. Omega should be within 0 and 2, and we looked at hunting, we looked at a few demos, you have tried it out, okay, right, and we found that for Laplace's equation at least, that omega is very close to 2. What was the other thing that we did? Anything else? Laplace's equation. Then we looked at what is the convergence rate basically, right, we looked at how quickly does it converge, and indeed we found that then, because again using the same principle, we found the keyword that you used is error, we found out what is the error, and we basically, once we got the expression for the error, we asked the question how quickly is it decaying, and that gave us an idea of convergence rate. In a funny fashion, I introduced the ideas of eigenvalues and eigenvectors and the spectral radius, the largest eigenvalue, right. So rho of A or rho of, I think if I remember right, I called the iteration matrix P sub j for Jacobi iteration. Rho of P sub j is the value of the largest eigenvalue or the largest eigenvalue, okay, the magnitude of the largest eigenvalue. It is called the spectral radius of that matrix, and we basically showed that you want the spectral radius of the matrix to be less than 1 for convergence. That is fine, but that is not enough. That's okay if you are saying does it converge eventually, but eventually is not good enough, right, and we found that actually for this class of problems rho of Pj is extremely large, it is very close to 1, it is very close to 1. So there are some issues there, okay, there are some issues there. SOR is one of those things that sort of helped us fix that issue, but there are some issues there. Then what did we do? We changed gears and looked at linear wave equation, right, we looked at linear wave equation. Linear wave equation, Laplace's equation is averaging, right, averaging basically means if there are differences you eliminate differences. Linear wave equation was different. Linear wave equation is propagating, whatever there is carried, it is like a stream. The example I gave was stream of water flowing, add chalk dust is carried at that speed, okay. So linear wave equation basically looks like and we tried a variety of schemes for this, just like things worked for Laplace's equation, we just tried a variety of schemes for it. That was sort of deliberately set up because I wanted to make sure that since Laplace's equation everything worked, I wanted to do the same thing, and we obviously know that they are not going to work. We tried forward time central space, which was unconditionally unstable. So the stability analysis, we looked at the von Neumann stability analysis, right, we basically linearized stability analysis, anyway it is already linear so it does not matter, but we added, right, we looked at the same kinds of exponentials that we looked at when we were looking at the error term here, and showed that forward time central space was unconditionally unstable. There was nothing that you could do, right, forward time central space was unconditionally unstable. And in all of this discretization, of course, we came up with a parameter which we called sigma, which was the Courant-Friedrich-Levy number, okay, and this number turned out to be pretty critical, right. So anyway, maybe I am getting a little ahead of myself here. We also did FTFS, I shouldn't forget that, which is also unconditionally, and then finally we did FTBS, forward time central backward space, and basically showed that if the Courant-Friedrich-Levy number is less than 1, that is, we had a condition, we got a condition. FTFS in fact basically gave us the idea, and from here we got the idea of upwinding, that is, FTFS did not work but FTBS worked because A is positive, and if the sign of A changed, if A became negative, then FTFS would work and FTBS would not work, right. So the equation is propagating U in a certain direction. I generally use the word some information, but your equation is propagating U in a certain direction, and your scheme also, it looked like needed to propagate U in the same direction. Is that fine? So to which we asked the question, so what is the difference between FTBS and FTCS? Well, I guess before we did that, what did we do after that? We looked at the modified equation. We asked ourselves the question, what is the problem that we are actually solving, right, and we got from that the modified equation. The modified equation looked something like this. It had terms which were of that form, higher order derivatives. So we asked ourselves the question, what would each one of these things do? In fact, we looked at it up to the fourth derivative, and we concluded that the odd derivatives are dispersive in nature for this equation and the even derivatives are dissipative in nature. Whether the U decays or is amplified depends on the sign of U and the nature of the derivative. So in this case mu2 has to be positive, in this case mu4 has to be negative, that is what we concluded, okay, right, and this is just dispersive. So we saw decay and we saw dispersion. Dispersion basically means high frequencies and low frequencies travel at different speeds, okay. So which was a very critical, very important phenomenon, okay, different frequencies travel at different speeds. So then we came back and asked ourselves the question, what is the difference between FTCS and FTBS, how come this works and this does not work, and we realized the difference was that in one case the mu2 was negative and the other case the mu2 was positive for the modified equation. So the natural question was, can't I just use FTCS and add a little amount of artificial viscosity, okay, which we have tried, it actually works fine, okay, and that FTCS, the relationship between, so any scheme literally can be written as FTCS plus an appropriate correction, right, if you choose to do it, okay. So that is as far as, so from here did we do anything else with linear wave equation? Then we looked at the quasi-linear wave equation and showed that and of course the general form where f is a function of u, and we showed that in this case right, where there were no discontinuities to start with, and the original function is smooth, the initial condition is smooth, the discontinuity can form. So which is an interesting combination. On the other hand, you have diffusion or Laplace's equation kind of, which is averaging out and eliminating discontinuities. High frequencies are decaying faster than low frequencies, that is one of the outcomes of this, which I forgot to recollect, important outcome. High frequencies decay faster than low frequencies. So that being the effect of the right hand side, this was just interesting that this was creating the high frequencies, right, and I pointed out that if you have in a different context, I had pointed out that if you have u dou x, and if you substituted sin theta, if u was like sin theta, then dou u dou x is like cos theta, so sin theta cos theta is like sin 2 theta. So there is a mechanism that increases the frequency, that doubles the frequency, which is very critical, okay. So this quasi-linear, this term seems to do that, it seems to increase the frequency. On the other hand, this seems to try to decay, and that combination is what of course makes fluid mechanics so interesting, okay. So then from here what else did we do? Of course we derived the, if you get a discontinuity, it is called a shock, and we derived the Rankine-Hugino conditions for the shock speed and so on, fine. Then what else did we do? We looked at one dimensional flow, we derived the governing equations, looked at one dimensional flow, we tried the FTCS plus dissipation for it, right. We tried first of all to make the equation look like this linear wave equation. So we got it in a, so we wrote it in two forms, we wrote it in a conservative form and a non-conservative form. Maybe I will just write the equation. Dou q dou t plus dou e dou x equals 0. Q was rho u, rho total energy, and E of course is rho u squared plus p, rho e t plus p times u, okay, right. These variables are said to be the conservative variables, it is written in a divergence free form, mathematically said to be written in a conservative form. For us of course from gas dynamics we know that across a shock these quantities are conserved, so you can give any reason you want as to why you want to call it the conservative form, but these are called conservative variables as a consequence, even if you write it in a non-conservative form. So you can still write this in a non-conservative form in sort of a desperate attempt to make it look like the wave equation, linear wave equation, right, where this term the flux Jacobian is dou E dou Q, okay, the flux Jacobian is dou E dou Q. And then we said, oh, the system is coupled, isn't there something that we can do to decouple it? We tried to change the variables from Q to Q tilde, which was rho u p, and that did not help either, that still gave a coupled system of equations, dou q dou t plus a tilde dou q tilde dou x equals 0 in terms of Q tildes, which are not non-conservative variables, a certain combination. Of course we could have used rho u t also, right. So and it turned out this was still coupled. Then we said, hey, wait a minute, I can relate these two to each other with a similarity transformation. I can transform this equation to this equation, and the A and A tilde will be related through a similarity transformation. Then we asked ourselves the question, is there a transformation that will diagonalize the matrix, right. So if you use the modal matrix of A or you use the modal matrix of A tilde, the matrix made up of eigenvectors of A, then it is actually possible to diagonalize it, and we got the characteristic form, okay, where the system of equations was diagonalized and it was decoupled. Right, so we got three equations that were basically propagating, they were propagating like the wave equation, okay, right, but not linear wave equation because they happen to, it is a quasi-linear wave equation, but at least our analysis would work. And the CFL condition for this, if we do a discretization and we got the Courant number, at least the Courant Friedrich-Levy number would be of the form u delta t by delta x, that would be sigma, I guess you could say u plus a or mod u plus a or whatever, that would be the largest Courant number. Am I making sense? Okay, and the typical stability condition would require that this is less than 1, is that fine? Okay, we are using mod u because u can be positive or negative, a is the speed of sound, okay. Are there any questions? Anything else? What did we do after that? We looked at the critical part of applying boundary conditions, and applying boundary conditions we decided to use the fact that this equation is propagating in a certain direction determined by A. So at a subsonic inlet, so the eigenvalues or the lambdas in that equation were u plus a, u minus a, where a is the speed of sound. So at a subsonic inlet these two are positive, that is negative. So at the inlet these two are propagating into the domain, this is propagating out of the domain, and we use that to determine boundary conditions. So typically at the inlet we applied for flow through a pipe P naught and T naught at the inlet and P ambient at the exit. Because at a subsonic exit this is negative, this is positive, these two are positive, so these are propagating out of our domain at the exit, whereas this is propagating back into the domain. Am I making sense? Is that okay? Fine. So we needed 3 quantities, we have developed we have got 3 quantities, but actually at each point we need to get 3 each. So we have to get 3 more, right, which we did by extrapolating. So if I actually write the domain and show the grid points, the first grid point and the penultimate grid point and the last grid point, then we basically said that there are certain quantities that have to be extrapolated, and we explored various things that you could use to extrapolate to the boundary, right, and this is very important. So the emphasis here is there are boundary conditions that you recollect, there are boundary conditions that are required by the physics of the problem. Your pressure vessel, the air in it has a certain P naught, it has a certain T naught, these are measurable quantities. You have a pipe, you have a valve, there is an ambient pressure, you open the valve, the ambient pressure and the P naught basically determine what is the speed with which the air is going to flow. Am I making sense? And the T naught will help you determine the other parameters. That is what the physics requires. The mathematics basically says that you need 3 quantities because plus an initial condition, because you have a single time derivative and you have a single spatial derivative, first order spatial, first degree spatial, and we have 3 quantities. But the numerical algorithm insists that you need q here and q there, and therefore you have to generate, the numerics requires more boundary conditions. So we have to actually generate those boundary conditions, we have no choice. Is that fine? Okay. So then of course we also wrote, one important thing that we did was we wrote this in the delta form, and this is a, we wrote the equation in delta form. I will just write one as I said, none of these are just to recollect, where R is the residue. So I have not defined in the recollection, I have not defined the residue so far. The residue is if you have an equation and you substitute a potential solution into that equation, if the right hand side does not match, whatever is left over is called the residue. Okay. So if you have LU equals 0 and you substitute a candidate U and you do not get a 0 but you get some value, that is called the residue, whatever it leaves is called the residue, that is the residue from the steady state Euler equation, and this is the delta form. This is the correction to the current state in Q that you have, current candidate solution that you have. The big thing that we want to take from here is that given this R will determine if you reach the solution or not. If the residue is 0, your current state is correct. If the residue is not 0, your current state has a problem, needs to be corrected. You can use this, solve the system of equations to determine the correction. If the residue is 0, the correction will be 0. If the residue is 0, the correction is 0, as long as this is not singular, it can be anything, and therefore it is possible for us to choose something that will make the convergence faster. That was the other deal that we had. So we do this carefully because this determines when you reach the solution. You do this carefully because that will determine how fast you get to the solution. Is that fine? Okay, right, and then we did a little more involved boundary conditions, application of boundary conditions here, right, converting it to characteristic coordinates and so on. Okay, is that all? Did we do anything in the, then I wrote out the equations for the quasi 1D, right, quasi 1D, and that was basically about it, right. What did we do after that? We looked at unsteady flow. What did we do after we looked at, I think we spent a little time on unsteady flows, right. We did the preconditioning the unsteady term. Is that the deal? Is that what you said? Yeah. So we use this. See, there is a certain freedom that this gives. This argument gives. That's the reason why I want to emphasize this. That is, this determines that you have the solution, and therefore, if this goes to 0, the correction goes to 0, and therefore whatever multiplies it goes to. See, that gives you a certain degree of freedom. Then we look at it and say, if I am looking for the steady state solution, dou E dou x goes to 0, right, dou q, if you look at for the steady state solution, dou q dou t goes to 0, and therefore if I multiply dou q dou t by some matrix, it does not matter. So why would I do that? I do that because the eigenvalues happen to be u plus a and u minus a, and the problem gets difficult when either u minus a is close to 0, it means you are going at transonic speeds, near transonic speeds, or u itself is 0. The problem becomes extremely stiff, the eigenvalues become very disparate, the propagation speeds become very disparate. So by pre-multiplying this by gamma, it is actually possible for us to precondition the problem. and if since I am looking only for the steady state, this pre-multiplying by gamma dou q dou t does not really affect the steady state but affects the rate at which you are going to reach it. The same idea as that, right. There is something going to 0, I can multiply it by whatever I want as long as it changes the algorithm so that I get there faster, but where I go is the same destination, that is the key, okay, that is the key, is that fine, right. Then of course we looked at unsteady flows by adding a pseudo time term, right. Of course you can solve this directly using, I think post my demo I did Runge-Kutta method, right, and you can solve this equation without the gamma, of course, if you are looking for the unsteady solution, you can solve this directly. So if you are looking only for the steady state solution, this is called a time marching scheme. If you are looking for the transient, we are looking at a time accurate computation. You could use Runge-Kutta or whatever it is, but what we said is, oh, we have built up so much machinery for steady state solution that if you add a pseudo time term dou q dou tau, and you could then, because that is going to 0, multiply that by a preconditioning, right, you could actually converge to the steady state in tau and get the unsteady solution in real time that you want, okay. So we were then talking about acceleration schemes, right, and then we went back and basically remembered that high frequencies decay faster than low frequency. We recollected all of these things, and of course in my review I think I have left out representation of functions, the demo that critical demo that I did of high frequencies and low frequencies, but it does not matter, right, that high frequencies decay faster than low frequencies, right, and we basically came up with the multigrid scheme. So the demo that I am talking about is where we represented sin x using the demo. I recollect the demo, I will go back to the demo. We talked about representing sin x using hat functions. That was a critical demo for us because it showed that for a given grid there was the highest wave number that we can represent, that is very important, or turning it around, whether a wave number is high or low depends on the grid that you are talking about. And if you say high frequencies decay faster than low frequencies, then you are interested in using a coarse grid because the wave numbers then become higher frequencies. What are low frequencies on a large grid become higher wave numbers, right, on a coarse grid, hence the multi-grid scheme. So what you basically do is you use grids of different sizes, right, you use grids of different sizes, h, 2h, 4h, 8h, and you transfer the residue. This is the critical part. You transfer the residue from the fine grid to the coarse grid, and you transfer the correction from the coarse grid to the fine grid, okay. So it is possible for you to actually go through this process of transferring the problem, in a sense, by you transfer the residue, you are transferring the problem, transfer the correction, you are transferring the solution, in a sense, if you think about it, okay. So it is actually possible for you to run your program on a very coarse grid, you run your problem on a very coarse grid to eliminate, so that you convert what seem to be low frequencies on h to a relatively high frequency on 8h, is that fine, okay. So multi-grid schemes, of course, and then we said, oh, there is possible actually, in fact, why would we do that? You would just basically start with a coarse grid and transfer. In fact, when we talked about Laplace equation in the beginning, that is one of the things that we suggested, that compute the solution on a coarse grid and transfer it as an initial condition on the finer grid. So you could actually do this here. You can start on the coarse grid, iterate a few times for Laplace's equation, or take 10 time steps for Euler equations or whatever, and transfer it to the next finer grid. So you could actually go from 8h, 4h, 2h to h, and then go through this process. And typically the critical thing that you want here is, what is the thing that we have to recollect here? Work units. That's what you always, work units, that one sweep on the finest grid, right, in one dimension is equivalent to 2 sweeps on the coarser grid, is equivalent to 4 sweeps, and if you go to multiple dimensions, of course that gets even better, right. So you would expect that in 3 dimensions multi-grid will work extremely well, right. The convergence rates that you will get in wall clock time, how quickly you get to the solution will be much better. What did we do after that, after multi-grid methods? calculus of variation. We looked at so calculus of variations basically comes back and says, so we are back to this business, I am representing a function. The only thing is now you actually have a measure of something. So you say that I have if I think the example that I gave is if you are coming from your dining hall to its classroom, what is the shortest path that you, so you can come up with some kind of a measure or a metric to see which is a function that you want. Like you are looking for you have a functional, you have a measure and you want to minimize that measure, and from there we derived the Euler-Lagrange equations. We showed then that the relationship between the variational problem and the differential equation, right, because it involves optimization, there is a differentiation and setting equal to 0 kind of a process that you do to get the Euler-Lagrange equation. So in that sense the Euler-Lagrange equation is like a derivative, right, the Euler-Lagrange equation is like a derivative, right. So you differentiate, find the first variation and you get this derivative, and we showed that Laplace's equation, we looked at the variational form of Laplace's equation and showed that you could get Laplace's equation directly, which was analogous to the earlier Ax equals b being a minimization of a quadratic cube. It was analogous to that, okay, and we basically said that yes, so it is possible for us sometimes to solve it in the variational form. If you get the variational form, the amount of smoothness required of the function is not as much, the smoothness required of the function is not as much, you do not need as many derivatives, right. So it is possible for us to reduce the derivative requirement, fine, and very often the expression in the variational form is simpler than in the differential form, very often that is so, but it is not always easy to get the variational form given the differential form, okay, you do not get something for nothing, right. So there is an element, there is a difficulty in doing that, okay. And finally of course we end with today's class, so I will just recap, put it on the back to the big picture. So the big picture possibly is that this is the reality as we see it. So you have right, and of course I have put this little brown to indicate, and from here reality you get this is the perception, this is what you see, so this is what it is. I just draw some, I can draw anything there because we can't see it is what I am saying, right. This is the perception, and from this perception we can abstract out a model. It would be ideally in a figure that I drew, it would be an exact circle, right, because we have with mathematical precision we abstract out a model, and then of course we can't even solve the model, we can't even get this model, so we end up doing a computer program which is discrete. The idea is that's pictorially that's what I am trying to represent here. So this is modeling, this is discretization if you want. You can check consistency, whether this model is consistent with this. As the number of sides of that polygon increase, does it become the circle, that is consistency, and you can do validation, you can check, perform an experiment and you can check whether the result is fine. Can't do that, the scientists and everybody constantly trying to do that, am I making sense? And of course here there is a test that you would do here also, you can add terms, remove terms, oh the flow is inviscid, the flow is viscous, right. So all of that stuff is happening here, but once you decide to do the Euler equation you go back here. So there are two possibilities, either you say this solves this and therefore I validate there, but you look at this, you know they are not. So validation is validation, that is it, right, and no more than that, fine, okay, thank you very much.